post next homework yet?
No, I was about to say I'll post some homework by Wednesday for next week. And that'll be primarily on recursion. So let's talk about cardinality for a minute, because there was some discussion about that, and I said we could talk about it. So cardinality of the integers, that's what we call aleph naught, and that's synonymous with saying that z is countable.
Does that look different on a computer? Aleph naught?
Probably looks fancier.
Okay, but what is it supposed to be like an A shape or an X shape?
It's like an A shape.
It's weird. It's like that's supposed to be like a diagonal but squiggly. And
Yeah, and there's supposed to be like
squiggles.
Something like that.
Yeah,
It's
weird.
really perfect. It's not.
If you don't recognize it, it's probably aleph. So when we say something's countable, we mean it's got a one-to-one correspondence with the integers. Okay? Any subset of the integers is also countable. Okay? The evens, the primes, the odds, the integers that are multiples of a billion. Those all have the same cardinality as z. Okay? Finite sets, the cardinality is just the number of things. So the set ABC, cardinality is 3. Infinite number of elements, cardinality is not infinity. Okay, it's only the number of elements for a finite set. For an infinite set like Z, cardinality is not the number of elements. It's this more abstract notion of size. And for the integers, we just use the symbol aleph naught. And it means it's countable. So anything that's countable and infinite is going to have cardinality aleph naught. So the rationals, we did this trick where you can write down integers on each axis. And then you can take ratios, 1/3, 1/4, 1/5, 1/6, 2/2, 2/3, 2/4, 2/5, and so on. And if we can order something, then it's countable. The one-to-one correspondence is the integer 1 maps to the first thing in our ordering, the integer 2 maps to the second thing in our ordering, and so on. And we can order the rationals by doing this diagonalization trick. Right, so we move over and we come down the diagonal, we move down, we go up the next diagonal, we move over, we come down the next diagonal. And if we encounter a number that we've already encountered, we just ignore it. And so taking that into account, this is rational 1, 2, 3, 4, this we've already seen, 5, 6, 7, 8, and so on. And that gives us a one-to-one correspondence. So rationals are the same as integers. But then reals, that has a cardinality that's strictly greater than the cardinality of the integers. So there's more reals in a very significant sense than there are integers.
And there was no name for the cardinality of the reals, right?
Was there equivalent to that?
Yes and no.
Yeah,
I
that's
think
fine.
Yes and no.
Uh,
So Aleph 1 is the smallest cardinality that's bigger than Aleph naught. Okay, it's the cardinality of the smallest set in some sense that's strictly bigger than the integers. And the cardinality of the reals may be equal to Aleph 1. That's the continuum hypothesis. Is that true or not? So if you believe that, then you could use that for the cardinality of the reals, but you'd start a bargaining fight. Cardinality of the complex numbers is the same as the reals, because complex numbers are basically like irrational numbers. You just need a pair of reals and you've got every complex. Just like irrational is all the pairs of integers. And so you can do a diagonal crossing out of complex numbers to see that these have the same cardinality.
What exactly is a complex number? Just like
A real part plus an imaginary part. So like a plus b times I, where I is the square root of -1. And the complex numbers are the things that kind of complete the real numbers in a mathematical sense. Any equation that we can write with complex roots, any polynomial with complex roots, all of the solutions are complex numbers. And that's not true with plain old real numbers. Because this, the coefficients are real, but there's no solution for this in real numbers. Your solution is plus or minus I. But if you move to complex numbers, you've got everything closed. Any polynomial with complex coefficients, all the solutions are complex numbers. All right, and the last thing that I think was in that note was closed interval versus open interval. And they have the same cardinality. But it's hard to define a one-to-one correspondence between these numbers and these numbers, because we've got a 1 over here and we don't have a 1 over here. And if we just map x to x, we can map almost all of these numbers to this interval, but we've got one extra number, and it's not clear how to map that into here. If we map it to 0, then we don't know what to map 0 to over here. But we can show that these have the same cardinality by showing the following.
Isn't this kind of like the 0.999 thing?
Sort of, but it's a little more insidious. We can show that both of these things are true pretty easily. To show this, we just need a one-to-one mapping from here into this set. It does not have to be surjective. It doesn't have to be a bijection between these. We just need an injection from here to here. And to show this is less than or equal to this, we need an injection from here to here. And those are pretty easy to come up with. And given these two statements, we can invoke something called the Schroeder-Bernstein theorem, which says, therefore, the cardinalities are equal. That's way more detail than you're responsible for on this stuff for tests. But since it came up in a discussion, I wanted to talk about it, because I love talking about it.
First one is easy, but I don't get the second.
How could the right possibly have a greater than or equal to cardinality than the one on the left?
This?
Yeah, I mean, I can understand it having equal, but not greater.
Okay, so to show that this is true, remember, we're not comparing numbers. Cardinalities are not numbers. This means there exists an injective map from here to here. Something that takes each one of these numbers to a different number over here. So there's an injective map. Did I do this backwards though? Yeah. That's the easy direction. Here's the harder direction. Right, so if this is smaller, we need an injection. If I had it right. Right, and it feels wrong because this feels like it has more numbers than this because it's the exact same set plus an extra number. But cardinality is not the number of elements. Okay, this symbol means that there's an injective map from here to here. A map such that two distinct things here go to distinct things over here. And f of x equals x over 2 is such a map. If we have two different numbers here, they'll have different values when we divide by 2. And every number from 0 to 1 inclusive does lie in this range. It actually lies between 0 and 0.5. So that mapping confirms that this is the case. And to show this is the case, we simply need an injection from here to here, and f of x equals x works fine. And so we know this is true and this is true, and then Schroeder-Bernstein theorem says, therefore, cardinalities are equal.
So, I know that f of x equals x over 2 does work in this case, intuitively.
Yeah.
But how would you show that rigorously?
You need to show that this is defined for every value in here.
Okay.
And we know from what division is that we can divide any number by 2.
Okay.
We need to show that this always lies within here. And since x lies in here, 0 less than or equal x less than or equal to 1, then 0 is less than or equal to x over 2 is less than or equal to 1/2.
Okay.
And that means that it lies in here, because this is everything 0 and less than 1. And you need to show that if f of x equals f of y, x over 2 equals y over 2, x equals y, that's the definition of injectivity.
Okay, cool.
The freaky thing is that none of this helps us find a one-to-one correspondence between here and here, which is sort of our definition of having the same cardinality. Schroeder-Bernstein assures us that they do have the same cardinality, but it's not a constructive proof. We don't end up with a one-to-one correspondence at the end. We just end up with the knowledge that there is a one-to-one correspondence. I have no idea what it is.
Yeah, except for one value, though. Because one from
Because of that one, yeah.
So those are not countable. Anything that's any set bigger than aleph, cardinality bigger than aleph not
Is not countable, yeah. If it's countable, then it has cardinality aleph 0.
Ah.
And we're mostly sticking with countable things because discrete math is usually dealing with integers, discrete structures, deals with integer numbers of things. And induction, which we're in the heart of right now, is all about countable things. Because we're making propositions P of n, n's coming from the integers.
So it seems like the theorem, it's just kind of waving off that one and saying that, every analysis is a one-to-one correspondence, but I mean, we can ignore that one. That kind of what
That's the end result of applying Schroeder-Bernstein here. But I don't know the mechanics of how you prove Schroeder-Bernstein. I haven't dug into that. And I think there's some very elegant stuff going on in there. But if I were to try to find a one-to-one correspondence, I would possibly do something like right, I can show that those two things have the same cardinality. And I can believe that the cardinality of this is less than or equal to the cardinality of this. Because it feels like this has got fewer things in it than this. And I might work from there and try to get to something like this. But I suspect the mechanics are over my head.
Does any set of, or two sets of real numbers have the same cardinality since it's reals?
Unless it's countable. Like the set of real numbers that are equal to their integer value. That's a countable subset of the reals.
Oh,
2,
okay.
3, 4, 5, 6.
Yeah.
But other
this
than
case.
yeah, other than the weird cases, yeah, I think so.
Because yeah, so like 0 to 1 would have the same cardinality as like 0 to 100 million.
Exactly, yeah,
Okay,
yeah. And the set of irrationals has cardinality Aleph naught. The set of transcendental numbers, I believe, has, sorry, Aleph 1, or the same as the reals. Transcendentals, I believe, have the same cardinality as the reals.
What are those? Transcendental.
Pi, e, things that aren't the solution of polynomial equations. So square root 2 is irrational, but it's the solution of this equation. So it's an algebraic number. If it's not a solution of an equation like that, it's not algebraic, it's called transcendental. And you can prove there's no polynomial you can write whose solution is equal to pi. Crazy proof. That makes pi transcendental, e is transcendental. And apparently lots of things are transcendental because the cardinality is the same as the reals.
You're saying you can't find an equation to come up with, like what?
You can't find a polynomial equation whose solution is pi.
Exactly pi.
Yeah.
Okay.
Now you can find infinite series that if you evaluate them, they get closer and closer to pi.
Okay.
But a polynomial of some finite degree, x to the 10 billion minus 17 x cubed plus 3, never going to have a solution that's equal to pi. That's what makes it transcendental. Yeah.
No, like,
Okay. All right, so good enough on this stuff? Like I say, you might have a question like, you know, which of these has cardinality bigger than the integers? And I'll ask you about the odd numbers, the prime numbers, the real numbers, and a set of 3 dogs. Right? And I want you to have seen this stuff just in the hopes that you'll encounter it down the road and you'll remember something about cardinalities and that they're not the same as sizes for infinite sets, but that there is a notion of sizes. And this stuff pops up where you'd least expect it down the road, so it's good to have seen it. Postage stamps. The 4-cent and 5-cent postage stamps. And I said we could spin some code for this. And I saw some discussion where some people started some code, and I didn't check this morning to see how far that got. But how many people worked on an algorithm for actually, what did you come up with?
I just said, I tried to pull it up just now, I couldn't see.
Okay.
I
Is it on
just-
Canvas or?
Yeah.
Okay.
Discussions. Well, I had a loop that after it took in the first argument from the command line,
Mm-hmm.
it would take that and see if it was, if that minus 4 is equal to mod 5,
Okay.
or that minus 5 is equal to mod 4. Since there's useless amounts of,
Right,
you don't want
right.
to check against the same one, because then you know it's equal anyway. And I just had a multiplier in my counter, in my for loop,
Mm-hmm.
that would multiply the 4 or the 5 by my counter.
Okay.
So it would check until it found 1.
Okay.
It matched.
Cool. So sort of an exhaustive search. Cool. That works. Did That's a cool solution. So try combinations and get to the answer. When we showed that we could always do this, we did a few things. We said 15 cents is just 5 plus 5 plus 5. We knew that we could do it for 15 cents. That was our statement, P of 15 is true. And then we said if you can do it for P of n, we can show that you can do it for P of n plus 1. And we did 2 cases. Case 1, our solution for P of n only includes 5-cent stamps. And since we're at least 15 cents, we've got at least 3. So take away 3 5s and add 4 4s. That bumps us up a penny.
Couldn't you simplify the algorithm once you get above 20 cents? Because they're both multiples of 5 and 4. So you could just divide that and then solve it like it's a smaller number for the remainder.
Yes, that would be a good solution. So if you want to do this for 97 cents, we could take off 4 20s, and we know how to do a 4, how to do a 20. So we pull off 80 and we're left with 17 cents, and we solve it for 17 cents. So that would be a cool way to do it too. Break it into a few cases. Pull off a big chunk that we already know how to solve because it's a multiple of 4 or a multiple of 5, and just solve it for the remainders. So that's a cool solution too. I like that. Let me show you a not so easy, but perhaps also cool solution. So our proof here, if Pn only included 5s, you can take off 3 of those and we can add 4 4s. Otherwise, if Pn includes some 4-cent stamps, then subtract a 4 and add a 5. And that raises you by a penny. So if you're not terribly clever, we can write code for this using this proof method. So here's what I did. And because it's C and we pass things by value, I had to do a lot of asterisks and stars to be able to change the value of things. Don't get caught up in that. Here's what's going on. The real punchline is down at the bottom. But I'm going to say enter the desired total. I'll get the total. And go is my code that finds a solution. So I pass a total and it'll tell me how many 4s and how many 5s I need. And I'll print that out. Number of 4-cent stamps, 4s. Number of 5-cent stamps, 5s. And I'll just loop here forever. So if I run this, if I get 15, there's that. If I get 150, it's that. If I get 154, 153, too big. All right, so it finds solutions for us. But here's what I did. So this is just my main program that prompts me, calls my go code, and then generates the answer. Here's my go code. So if my total is less than 15, I'm going to print out an error message. And I'm setting my return value to 0 just because. So less than 15, that's not a valid case. My base case says if my total is 15, set the number of 4s to 0, set the number of 5s to 3. That's our solution that we know how to do. Otherwise, here's what I do. I solve the problem for total minus 1. And how do I do that? I use my go routine. So I say, for total minus 1 cents, how many 4s and how many 5s do I need? So I find the solution, P of n. And then I say, if I have any 4s, subtract 1 4, add 1 5. If I didn't have any 4s, subtract 3 5s, add 4 4s. And that's my new solution. So this is a direct coding of this proof.
Would you be able to make something like this if you wanted a variable number or a variable value for stamps, like 2 and 8, or
Sure.
I'm sorry, 2 and 7, or 3 and
Yeah, you could feed those things in the beginning. But you need to know what the magic is, which we were talking about last week, which I never got back to. But if I have a recursive proof that I can always find a value of Pf n plus 1, and in this case it's a constructive proof, I actually give you a way to solve the problem for n plus 1 based on a solution for n, I can code that directly. And the trick is right here. This is my function go. Right? That's where I'm sitting right here. All of this is my declaration of a function called go. But inside there, I call the same function go. But I'm trying to solve go for total cents. And in here, I call go for total minus 1 cents. And I'm not even adding anything up in here. I'm never like adding 4s and 5s together to see if I reach the sum. The only arithmetic I'm doing is either subtract 1 from the number of 4s, add 1 to the number of 5s, or subtract 3 from the number of 5s and add 4 to the number of 4s. And there's no looping in here, there's no while loops, there's no for loops. Because this is a constructive algorithm. So this is a recursive function. It's a function whose solution is expressed in terms of the solution of smaller problems. And if I put a print message in here, just to print out the word hello every time that I call my go routine. So if I run this and I try to find the total for, I don't know, 101, it called my go routine a whole bunch of times before it found this solution. This was actually calling it to solve the problem for 100 cents. And to solve that, it needed to call the problem to solve it for 99 cents. And to solve that, it needed to first solve the problem for 98 cents, all the way down till it called it for 15 cents. And my code said, oh, if it's 15 cents, just use 3 5s. And it returned without having to call go again. And once that returned, this call to go knew the solution for 15. It said I got 3 5s, let's take away 3 5s, add 4 4s. Now it had the solution for 16 and it returned that, and it worked all the way back up until it got to the solution for 101. You had a question?
Which way is it running? Like, do you solve,
Say again.
do you solve 15 first and then go up?
Ultimately,
Do you solve
well, let's
from
find
101
out.
and go down?
You solve 15 in the middle.
Yes.
It digs all the way down to 15 and then comes back up and then gives you the final.
So let's say we're solving for percent %d. And let's just solve it for 30. So it's trying to solve it for 30. To do that, it's going to call and it's going to solve it for 29, 28, and so on. And eventually, it's going to try to solve it for 15, and it is going to succeed. And then it's going to actually get the solution for 16, and then get the solution for 17, and so on. So it asks for the solutions kind of in descending order, and it finds the solutions in ascending order.
Why?
That's how I wrote the code.
Okay, but couldn't you solve for 15? And then, if it's all 5s, get rid of it, switch them all to 4s and add a 5.
You could start from 15, find the solution, and then say, okay, let's go from 15 to 16, you can work your way up too. And it ends up being the same set of steps that you're doing.
Okay, that makes more sense to me.
Yes, but I want to mess with your head.
That's pretty much the point of this class.
Yes. Good question.
It was actually one of the outputs that you had for a previous running of this. You ended up having a situation where you called for 321 cells.
No, I had some other numbers in the beginning
Okay.
that didn't.
I think I was wondering if it had to do with the sig fault you had just before it.
No, it was actually just a typo. So I typed 1, 2, and then it found my prompt 3, 2, 1.
So it solved
So it
for
was
1,
actually-
2, 3, 2, 1?
Yeah.
Okay.
So, does the memory, or does the computer store each declaration of go? And so, say for next 16, it goes solve for 16, I can't do that. So I actually go to 15 and wait for the solution. Once 15 gets the solution, 16 goes back.
Yes. So these arguments, total 4s, 5s, those are local to this version of Go. And if I call Go again, all my local variables, they have their own local value. When I call Go again, there's a new copy of those. And everything that happens in that new call to Go, once it's exited, I'm back to my old context. My old values are the same. The only thing that's different is I'm using the return value from Go to set 4s and 5s. So those come back from my recursive call. But each time you call a routine, you sort of freeze your current environment and you start with a clean slate over here, other than stuff you passed into it. And you gotta have that for this to work.
So what do the asterisks do?
That's just C silliness for dealing with addresses and pointers. Because C is passed by value, so if I just passed 4s and 5s, I wouldn't be able to change the value. So I pass the address by declaring that 4s and 5s are pointers to integers. And down here, when I say star 4s, it means the thing pointed to by it. That's just C weirdness.
But if you sit there and have it, the memory location declared in your main, and you keep pointing to that, wouldn't it be a global variable?
Then it'll be a global, right?
But you define.
But because these are arguments to my Go routine, it's got its own copy.
Can I see the, where you
Can you go back up to where you declare 4s and 5s?
Wait, go ahead.
Can you go up to where you go to use Go in main? Just-
Yeah, so Go and I pass the address of 4s and the address of 5s.
Okay, so that's why it's local.
Yeah.
Because you're passing in values for it, then Go stores those in another location to be local.
Mm-hmm.
Okay.
That's a lot of pointers.
So let me show you a better example without pointers and all of that stuff. Because now you got me doubting whether those are really local. We may have just gotten lucky, but let me show you a better example, which is not as exciting because it's more mathematics, but n factorial. So what is 1 factorial? 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3. If I want to write a program to compute n factorial, I just have to make a loop and multiply 1, 2, 3, 4 all the way up to n, right? But if I'm lazy, can do something totally different.
Can you keep adding the product? No, keep multiplying the product, but
Mhm.
until you get to n.
Yeah, that's the sort of normal way of computing a factorial. I want to show you an abnormal way of doing it.
Didn't we have this as a homework as an alternate way of computing factorials and proving it?
The previous homework?
Yeah,
Yeah, that was like sum of n times n factorial,
yeah.
which was, yeah, that was a different way of doing it, but I think we ended up with n plus 1 times something.
And plus 1 factorial minus 1.
Minus 1, okay.
First answer.
Similar idea, simpler formula. So if n is equal to 1, n factorial is just 1. If n is bigger than 1, n factorial is just n times n minus 1 factorial. Agreed?
You're gonna do this recursively.
Yeah. So let's compute 10 factorial and print it out. So if n is equal to 1, I'm just going to return 1. Otherwise, I'm going to return n times factorial n minus 1.
That's what I said.
Yeah. I thought you meant looping.
No, it's like recursive. If you
Yes,
the answer,
okay, exactly,
That's
right.
what I said.
Okay. What he said. So I'm going to use the same fact function to find factorial n minus 1. I'm going to multiply by n. That's going to be n factorial. So there's 10 factorial. And this isn't too bad. We can print out a message showing what it's trying to find each time. And again, it's trying to find 10 factorials. You do that, it's trying to find 9, 8, and so on, and eventually it tries to find 1 factorial, and it finds it, and then it pops back up through the recursive calls. Now, if I don't have this base case, right, it keeps trying to find the solution in terms of some other solution, and it never finishes. And what happened here was I actually ran out of memory. And so the program exited painfully.
Don't you
Yeah.
have to do something similar for like projectile motion with drag? Like,
Could.
Is that a recursive thing?
You can find recursive ways to express almost anything. I haven't seen that particular one, but I can imagine.
Because like in physics, we did a spreadsheet and it used the answer to the previous
Okay,
and like.
so you could think of a time series in general as kind of a recursive expression, right? The current state is a function of the previous state. And that's an interesting way to look at time, actually.
The drag spreadsheet, it's a good estimation, but it's not actually recursive, it's a little different. So you can use recursion to get something that's like 1 or 2% off, but it's not actually
Yeah,
the actual.
but in general, that's an interesting approach to thinking of a time series analysis. I haven't thought of it in terms of
It
recursion
would work for
before.
throwing a softball, but it would not work for flying an airplane.
Yeah,
I think that's how it's explained in that.
So Fibonacci numbers, which we'll come back to when we talk about probability and stuff. This came out of studying rabbit populations. It's a sequence of numbers. Each number is the sum of the two previous numbers in the sequence. So 8 plus 5 is 13, 13 plus 8 is 21. That's your 7th Fibonacci number, and so on. And you can write a loop to say, if I want to compute the nth Fibonacci number, just start from here and keep adding up. Remember what your two previous numbers are and generate all the numbers up till you reach n. But we actually define this series recursively as follows. Right, f of 0 is defined to be 1, f of 1 is defined to be 1. And if n is bigger than or equal to 2, f of n is just the sum of fn minus 1 and fn minus 2. Perfect setup for a recursive function. Hey, here's one right now. So here's my function fib. And let me be true to what I just wrote on the board. So if my number n is less than 2, I want fib 1 or fib 0, I'm just going to return a 1. Otherwise, I'm going to return fib n minus 1 plus fib n minus 2. That's what?
Butte F. F of n.
It's a big F. This one?
Yeah.
Yeah, it's just a capital. So, I'm not really doing any work in here, right? I'm not really computing elements of a series. I'm just using this definition. But it's a recursive definition. It describes the value of this function at n in terms of its value at smaller values of n. And by coding that up, I can find, say, the 10th Fibonacci number, which if you go through and you add these up, right, so this is 34, this is 55, this is 89. So let's put a print function in here and see each time that we call fib to compute the Fibonacci number of some value. Let's print out something that shows us what number we're working on. And so we're trying to compute the 10th Fibonacci number here. And that's all the calls that it made to our Fibonacci function. There's a whole lot more than 10 calls.
How do you know what n minus 1 and n minus 2 are? Because, like
So we call it the function.
No, it doesn't know, it just calls it again.
Yeah, I don't know what fib n minus 1 is, but fib will tell me.
oh, okay, so
It's calling the function there.
Yeah.
When it
it
returns.
keeps calling it until it gets to 1,
Mm-hmm.
and then it
He keeps calling it
back up.
to solve it.
Yeah.
Okay. And
So
then,
here's the thing with recursive functions. It can drive you crazy to try to actually trace through what's happening, but it's a good thing to do. We'll do this more in 222. But it's instructive to do so, but it's not necessary. If you believe that fib works for values less than n, in particular, if you believe fib works for n minus 1 and n minus 2, you've got to believe that fib will work for n, if you believe in induction. Because if this gives me the n minus first number and this gives me the n minus second number, this expression will give me the nth Fibonacci number. And at some point, that's all you need to believe. And the only reason that I believe this is because I know that if n is less than 2, the Fibonacci number is equal to 1. So I believe this will give me the result. And I believe if this works for n minus 1 and n minus 2, it works for n. That's the inductive step. So you can prove this actually works by using mathematical induction.
It seems like that is wildly inefficient though.
It's way more inefficient than you might believe. So let's generate the 20th Fibonacci number. And I can do it on the board in about 60 seconds. I just have to do 10 more sums, and I might not even need a calculator. If we take this approach with our computer, and we say generate the 20th Fibonacci number, let's look at what it does. And let me shrink my font and try to get back, and I can't.
So are recursive functions by their very nature inefficient? Or
They
is it
tend to
just-
be.
Because
We made a lot of calls, right, from there
I
all
was
the
gonna
way
say,
down to.
I'm looking at that printout, if I had a dime for every single time it says
Yes.
F1 or F2,
Yeah.
I'd be beat up by now.
So this can tend to be really, really inefficient, but the trade-off is it's trivial to write.
Shouldn't it just increase linearly with n?
If you and I do it, yeah, to compute fib 20 takes 20 operations.
Isn't that basically what it's doing? Except
No, it's not.
slowing that down and
It's
then back up?
calculating every single.
It's doing what we did when we tried to tile with those L-shaped tiles. We said, well, I don't know how to tile a 32 by 32, but I know how to tile a 16 by 16. And so it tiles this 16, this 16, this 16, this 16. But to tile that 16, we said, well, I don't know how to do that, but I know how to tile an 8 by 8. So it tiles 4 8 by 8s. And then it moves to the next 16 by 16 and it tiles 4 8 by 8s. And you keep redoing the same work, right? So as Ian pointed out, we're computing f of 2 and f of 6 and f of 4 over and over and over again.
Because it's not saying like for F6 I need to add F5 and F4. It's redoing all the work all the way back down to the base case over and over and
Yeah.
over again.
It finds f6 equals f5 plus f4,
So its inefficiency is growing exponentially essentially.
and then when it tries to find f7, it has to find f of 6 plus f of 5, and to find f of 5, it's going to do f of 4 plus f of 3. So it's doing f of 4 there, and it's doing it there, and it's doing f of 5 here, and it's doing it here. And every time that it tries to use f of 7, it's going to do all of these things again.
So it seems like, at least in the Fibonacci case, it would be miles simpler, or not, I don't know, simpler, but miles more efficient to use like an array or something, or a constant array where it saves the Fibonacci numbers to that array. But is there any situations where a recursive function is more efficient than using an array or something like that?
Well, using an array, if we use an array to store these values each time that we calculate them, that can't be less efficient than not storing the values, unless you're talking about just, execution time with an assignment statement. But no, that's what we're going to do in 222, something called dynamic programming. And the whole idea of dynamic programming is to try to save this overhead. Each time that we calculate a value, we're going to save it in memory. And the next time we need f of 5, instead of calling fib 5, we're going to say we already did that once, what's the value? And that's going to turn this into a really speedy algorithm. And for problems like towers of Hanoi, and
We
You
still
keep
haven't
hinting.
discussed it.
which we still haven't discussed, and tiling 2 to the n by 2 to the n regions and so on, for these problems that are so easy to solve recursively, we'll be able to use a combination of recursion and dynamic programming to do an efficient recursive solution. That's something we'll spend time on next term. But tomorrow, we'll do towers of Hanoi as our last recursive example.
I will hold you to that.
And you can hold me to that, and then we'll move on to counting and pigeonhole principle. All right, I'll see you later.
Recursion's quite efficient when you